find here problem number 2.1, okay, and I'll make a statement like this, okay. The statement is if potential is symmetric, okay, potential is symmetric, wave function will be alternatively symmetric and antisymmetric. Your eigenstate or stationary states E1, E2, E3 or Psi1, Psi2, Psi3, they will be alternatively symmetric or antisymmetric. Ground state will be symmetric actually. You can make a theorem out of it. Is that okay? Problem number 2.1. Again, if a potential is symmetric, okay, that means V of minus x equal to V of x. You can talk about symmetry only when your region of interest is symmetric about y-axis. Is that okay? Otherwise, you can't talk about symmetry at all. If potential is symmetry, your psi n of x, whatever you solve, okay, so these are alternatively even and odd. Is that okay? They are alternatively even and odd. Ground state being always even. I'll grab some theorem, okay, from I think R. Shankar, okay, that's the best idea, so that will be helpful for our problems, okay. Ground state being always symmetric, okay. This is so take a kind of note on problem number 2.1, okay. And I hope you know problem number 2.2, isn't it? Energy should exceed minimum value of the potential. E should exceed minimum value of V of x to have normalizable solution. This is also needed, okay. We are going to use this one. Energy should exceed minimum value of the potential to have normalizable solution. Only normalizable solutions are physically realizable, isn't it? That's why we are restricting. Again, we are always restricting ourselves to normalizable solution, okay? Yes, that's why energy should exceed minimum value of the potential. This is another thing that you need to keep in mind. Now I'll go to infinite square well, or simply we call 1D box or infinite square well. Particle in infinite square well, okay. Now look at here, our aim is to solve this one, minus h bar square by 2m d square psi by dx square plus v psi is equal to e into psi. If you solve this one, that means you got the total solution, am I right? In case of time independent potential, if you solve this one, that's done, isn't it? So along with that one, just put e power minus I e t by h bar, you got psi of x comma t, isn't it? And linearly combine them, you get most general solution. So that's why our aim is to solve this one. So to solve this one, this potential should be specified, am I right? Now infinite square well is one of the problem where we first specify potential. Is that okay? If you know the potential, you can solve the differential equation according to the given situation. Is that okay? Now look at here, this 1D box or this infinite square well, the physical situation is particle is trapped in some region. Is that okay? The idea is, look at here, we are going to symbolically draw our potential like this. V of x. So we are going to say it is walls of infinite height, okay, 0 here, a here, okay, particle which is trapped from 0 to a, okay, where you have walls of infinite height. That means your potential is infinity here, infinity here. Particle cannot enter in this region at all. Is that okay? Particle cannot enter in this region at all. Is that okay? Your V of x is infinity here, V of x equal to 0 here. There is no force, but particle is trapped. There is no force on the particle, but particle cannot go outside the region 0 to a. Now how do you define this potential? This potential you can define like this. V of x is equal to, it's equal to 0 when x is between 0 to a, it is infinity otherwise. Particle is free to move in some region, I mean that region is 0 to a, particle cannot go outside, that is the meaning. So we call this as hard walls, actually, infinite walls of infinite height, okay? But it's not true. So, I mean the problem is only one dimension. Okay, this is 0, this is x-axis, okay? Problem is only one dimension. We are going to imagine like this. So there is a wall so that particle cannot go outside, okay? Particle moving in one dimension and it is trapped between 0 to a. This is the physical situation. Yes. No, there is no practically you can't have infinite potential at all. But we can learn a lot of things out of it. We can learn a lot of property out of particle in an infinite square wave. And with some modification, we can apply that one to nanoparticles, these quantum dots like that, with some approximation. But in real sense, there is no infinite potential, okay, in nature. Is that okay?
So this is a modeling or what?
This is hypothetical problem, but with some approximation, we can apply that one to nanoscience. Is that okay?
Approximation.
With some approximation, where you will not have infinitely height walls, okay? So you have finite what you call barrier. Is that okay? So like that. Yes. Now look at here. One thing that you need to remember. I hope you have written this one. Okay. V of x is equal to 0 when x is between 0 to a, infinity otherwise. Okay. One thing that you need to remember here, let me plot what you call, what is the nature of my wave function, am I right? That I need to see. 0 here, a here, okay. One thing that you need to remember, what is this psi? This psi is the solution of time independent Schrodinger equation, am I right? Minus h bar square by 2m d square psi by dx square plus v psi is equal to e into psi, am I right? This is a solution of second order differential equation, okay. Now look at here, that's why this should be always continuous. Psi should be always continuous. This is the theorem we can take. Psi is always continuous. I mean, if it exists, it should be always continuous. Yes?
Sir, at the point 0 or a potential should be infinite.
Yeah.
Why you write v of x equals to 0?
Where I have written v of x? No, it's a kind of limiting point, okay? Just after 0, you have 0 value. Just before that one, you have infinity.
So then v of x 0 limit is 0.
Is that okay now?
Yes, sir.
No, both are same. That's what I'm saying. It is just to say that whether 0 is positive or negative. Whether 0 is positive or negative. Neither positive nor negative, isn't it? It's a kind of just after 0, your potential is 0. Just before 0, you again at 0 and then again. If I say after 0, before 0, then the question comes, what is at 0, isn't it? That's why both are same, okay? Both are same. It doesn't matter, okay? Yeah. Now look at here. Psi is always, or which psi should be always continuous. Remember this part. So that's why, look at here, physical situation is particle should be in this region, am I right? Somewhere between 0 to a, okay? Physically, particle cannot enter here, cannot enter here. That's why your wave function should be 0 here, 0 here. Is that okay? If I plot wave function, that wave function should be 0 here, wave function should be 0 here. Wave function can be some value here, okay? I don't know the value of what is the wave function. We need to solve that one. Is that okay? But wave function should be 0 here, wave function should be 0 here. Is that okay? So that means wave function should be 0 at x equal to a, wave function should be 0 at x equal to 0. That you need to observe. If it is not 0 here, so suppose suppose if wave function is not 0, suppose look at here. Yeah, so wave function is 0, that's a physical situation, okay? Suppose again inside this region, wave function should start from 0 actually. Is that okay? It can have any value, okay? Inside that region, wave function should start from 0 and it should end at 0 here. Because after that wave function is 0, before that wave function is 0. Continuity of the wave function requires that wave function should be 0 at x equal to 0, wave function should be 0, psi of 0 is equal to 0, psi of a should be equal to 0. So these two will be a kind of boundary condition or a kind of initial condition to solve what you call Schrodinger equation. This is because of physical situation, okay? Not only physical situation, one more mathematical condition is also there, okay? I mean, psi should be continuous, okay? And one more thing is psi is 0 here, because particle cannot go outside at all. Then probability of finding the particle here and here should be 0. That's why wave function should be 0. Is that okay? If wave function is 0, so wave function should be continuous. That's why wave function should start from 0. Suppose inside the what you call well, suppose wave function start like this. Then look at here, it is discontinuity.
Sir, so this wave function 0 means 100% 0 or
100% 0 only. Again, that's how we defined the potential. Am I right? Particle is trapped here. Particle cannot go outside. That's why we put infinite potential outside the region. Is that okay? It's not like harmonic oscillator. You may be thinking about harmonic oscillator. Not like that. Okay, there you have finite potential. Okay, outside the region. So now look at here. If a wave function happens to be like this, then look at here. You got discontinuity. Am I right? That will never happen. Okay. So that's why, because of continuity of the wave function, since wave function should be 0 outside the well, wave function should be 0 at the edge of the well. Okay.
Sir, we find the solution of Schrodinger equation at this point 0, or we are assuming some theoretical basis that wave function is 0. Sir.
No. What I am saying is wave function should be continuous because it's a solution of second order differential equation. Okay. Can you hear me? Okay. One more thing. Again, wave function is 0 outside, isn't it? Then wave function should start from 0 here. Otherwise, this continuity will not be followed, isn't it? It should touch 0. Again, whatever the functionality you have, it should touch 0 at x equal to a, at x equal to 0 inside. Is that okay?
So potential is infinite. That's why without solution of Schrodinger equation, we are assuming that wave function is 0 here.
Yeah, again, you can say because of potential is infinite, because of the fact that particle do not enter here and here, wave function is 0. You don't have to solve Schrodinger equation at this point and in this region. You don't have to solve, wave function is 0. We know that particle is not there, 100%. Particle is not there. Is that okay? And particle is somewhere here, 0 to a. Is that okay? So that's why, so we are going to restrict ourselves to 0 to a. Okay? So between 0 to a, your potential is 0. Am I right? Where the particle is. In that region, we shall solve Schrodinger equation. What is this one? Minus h bar square by 2m d square psi by dx square plus 0 into psi is equal to e into psi. Isn't it? We don't have to solve Schrodinger equation in this region or in this region because we know particle is not there. Yes.
what will be the potential in the region? Potential means
Potential is 0 here. I said it's a trapped situation. Mathematically, we have written like this, isn't it?
what is potential?
Again, now look at here. Particle is trapped, isn't it? That means it can't go outside. To impose that condition, you need some force, isn't it? That force is, again, this potential is derived out of that force. That's what I'm saying.
So we can say potential is the function of space at some point.
Yeah, again, potential is a function of x only. What I'm saying is, suppose if you have a what you call situation, suppose if you have a metal nanoparticle, okay, that surface again, that free electron inside the atom cannot go outside, isn't it? Then surface will what you call impose some condition, isn't it? Some force on the particles inside. Particle can be freely so roam inside, it cannot go outside, isn't it? That's the situation. So that situation that I'm talking about. Here particle is free, there is no force, but particle cannot enter here. But the situation here is particle is trapped here, okay? Here there is no force. Particle is trapped here. The best idea is free electron in your metal, isn't it? Okay? So it is trapped inside that one, isn't it? It cannot come outside that easily. Are you getting my point? You may need to supply large energy to so kick off an electron outside the metal, isn't it? So that's exactly the same idea. In the real situation, suppose even if you take metal, okay, your potential is not completely infinite. This is quite hypothetical. Saying that potential is infinite, you cannot take particle outside, that's quite hypothetical. But we can learn a lot of things out of it. Is that okay? In the real situation, you can have very high barrier, just like in case of metal, okay, not exactly infinite potential. Is that okay? Yeah. Now look at here. Yeah. Any question? So since our potential is 0, I can just rewrite this equation: d square psi by dx square plus 2me by h bar square into psi is equal to 0. Is that okay? Let me take this space.
Sir, one confusion, sir.
Yes.
So one side you say that the psi is 0 at 2 8 points. And to satisfy that, sir, v should be infinity.
Yeah. Suppose if you are worried, just take it like this.
Sir, but in given condition, yes, sir.
I mean, if you are worried, just rub out this one.
Yes, sir.
It's not like that at that point v is infinity, that's why it is 0. It is because of the continuity of the wave function. Are you getting my point?
So then one side, how can we write that potential is 0 at 2 8 points?
No, you are talking about, look at here, 0 here. Okay, I have 0 here. So before 0, look at here, you have infinite potential. After 0, it is free. Now, it's just like, look at here, I have similar situation. Just answer this one. Before 0, you have negative number. Am I right? After 0, you have positive number. Whether 0 is negative or positive. Like that, you have the similar situation here. Is that okay? So that's why, yeah, it's correct to say that whenever potential is infinity, your wave function should be 0. But it is one sharp value 0. I called x equal to 0, not 0 plus delta x, isn't it? So that's why at that point wave function should be 0. You can say that. So before 0, wave function is 0. That's why at that 0, wave function should be 0 to satisfy continuity. Is that okay? Or you can say, I mean, at x equal to 0, your potential is infinity. That's why wave function is 0. You can say like that also. Then you just rewrite this one. Both are okay. I was thinking about this one from very long time. Okay. Infinity otherwise. Don't write equal to. Both are same. Okay. It's just like to ask similar question that whether 0 is positive or negative. Okay. Yes. Now what we do is again, yes.
If we take from 0, then we can say that 0 is neither negative or positive. But
yeah, 0 is neither negative nor positive. That's why, now look at here. This problem will happen when you have discontinuity. Wait a second, I'll tell you. V of x, okay? It is values 0 here. Wait a second, let me explain. Thank you for that question. V of x is 0 here, okay? V of x is suddenly infinity here. Somewhere here I have infinity. It's a discontinuous function. V of x is a discontinuous function. For discontinuous function, at the point of discontinuity, you can't define function at all actually. Isn't it?
Yes.
At the point of discontinuity, you can't define that function at all. but wave function should be defined. Is that okay? So that is the situation happened here, that I haven't drawn like this, isn't it? Because how can you draw infinity, isn't it? So somewhere this height is infinity, it is going to infinity, think like that. So suddenly 0, isn't it? It is a v of x is a discontinuous function. In case of any discontinuous, yeah.
So infinity means we are putting lots of energy
To trap the particle.
to trap the particle.
Particle, that's correct. I mean physically, is that okay? Yeah. So now we are going to rewrite this equation d square psi by dx square plus just like omega square psi, isn't it? So we used to write like this. What happened? Plus k square psi is equal to 0, where we define k is equal to root of 2me divided by h bar. Is that okay? So that it's very easy to solve the differential equation, okay? So now your auxiliary equation is, how do you write auxiliary equation? D cap square plus k square operating on psi is equal to 0, where d cap is equal to t by dx, am I right? No, this is not auxiliary equation. This is a differential equation. Auxiliary equation is d square plus k square is equal to 0. It's a kind of assuming that it is polynomial in D, isn't it? Then what is D equal to? Plus or minus I into K, isn't it? D is equal to plus or minus I into K. So then what is your wave function? Psi of x. Let me write this, directly in terms of sine and cosine. Or you can write in terms of exponential, then you can convert in terms of sine and cosine. Am I right? A sine kx plus b cos kx. Am I right? Can I write like this? Yesterday we solved. Now look at here. A and b are constants. Okay, a and b are constants, and k value is given like this. Okay, k is equal to root of 2me divided by h bar. Okay, we need to find them using your condition, initial condition. Okay, now look at here. Psi of 0 should be equal to 0. Let me apply this one. 0 is equal to a sine 0 plus b cos 0. Cos 0 is 1. This gives b is equal to 0. First boundary condition. Is that okay? Once b is 0, let me write psi of x. If b is 0, it should be a sine kx. Am I right? So then apply second boundary condition. Is that okay? Then apply second boundary condition. What is that one? Psi of a should be equal to 0. That means 0 is equal to a sine ka. When you put x equal to a, wave function should be 0. If you put x equal to a, this should be 0. Is that okay? So what do you mean by this one? Observe very carefully. Let me rub out this part. I hope you understood this part. Observe very carefully. What do you mean by that one? A sine ka is equal to 0. Okay? Either a equal to 0 or sine ka is equal to 0. Isn't it? If a is equal to 0, b is already 0. If both a and b are 0, wave function itself is 0. If wave function is 0 throughout the region, then there is no particle. That cannot happen. This cannot happen. A cannot be 0. Okay, a should exist. B is already 0, isn't it? A should exist. So that's why sine ka should be equal to 0. Is that okay? So this gives us a condition that ka should be equal to, pick out, n pi, where n can be equal to 0, plus or minus 1, plus or minus 2, and so on. Isn't it? Now look at here. Okay, I got that one. I got what you call k value now. From this one, I got k value. What is k? K is equal to n pi by a, where n is equal to 0, plus or minus 1, plus or minus 2, and so on.
Sir, n equals to 0.
Yeah, 0 cannot happen, isn't it? Wait a second. I'll come to that point, isn't it? Now, if n is equal to 0, k, again, I better write psi of x. What is my psi of x? A sine k into x. Am I right? B is already 0. This is my wave function. We simply say wave function, okay? Time independent wave function, okay? Yeah. Now look at here. If you put n is equal to 0, k is equal to 0. If k is equal to 0, wave function is 0 again. Isn't it? We have to avoid that situation. Why? If wave function is 0, there is no particle at all. Isn't it? So that's why this cannot happen. Is that okay? I have written a mathematical condition, but that should suit our physical situation. Am I right? That's why I need to avoid n equal to 0.
So what is the meaning of this n?
N is some integer. Look at here. Meaning of this is sin k is 0 when k is equal to n pi. Trigonometry. N should be integer. N should be integer, either positive integer or negative integer. Am I right?
So this integer will not satisfy the
N is equal to 0 should not happen, because if n is equal to 0, what will happen? Our k is equal to 0. If k is equal to 0, wave function is 0 again. Is that okay? If wave function is 0, that means it is already 0 outside the box. Am I right? Inside the box also, if wave function is 0, what is there to study, isn't it?
Can you relate del n to quantum number?
N is quantum number only. We call this one as quantum number. Now what I am saying is, mathematically these conditions come, all conditions are not suitable for us. Are you getting my point? Speak out. Yeah. So that's why n equal to 0 should not happen. Okay. Now let me take n is equal to plus 1 and n is equal to minus 1. Okay. If n is equal to plus 1, so k is equal to pi by a. Am I right? Then your psi of x is equal to a sine pi x by a. Am I right? If n is equal to minus 1, k is equal to minus pi by a. Am I right? K is equal to n pi by a. Okay. So that's why psi of x is equal to minus, look at here, a sine minus pi x by a. What do you mean by sine of minus theta? Minus sine theta. Am I right? Minus a sine of pi x by a, isn't it? Check that out. Now look at here, corresponds to n is equal to plus 1 and n is equal to minus 1. You are not getting any different solution at all. This solution is same as this solution. Mod square is same, isn't it? Only mod square have got meaning, isn't it? Mod square is same. Or I told very earlier, if you multiply a wave function by minus 1, that will not change any of its physical property. Not even its normalization constant. Even after normalization, if you multiply by minus 1, you will not get any different thing at all, because mod psi square is same. Mod square of this one as well as mod square of this one, both are equal. Isn't it? So let me write e plus 1 here for minus 1 here. Am I right? Psi of minus 1 mod square is equal to psi of plus 1 mod square. Not only that, look at here. These are linearly dependent actually. One is negative of other. They are not linearly independent. Isn't it? One is negative of other. That's why, so if you take negative integer here, you are not getting any new solution. You are getting negative of this positive integer solution. That's why we are going to rule out this negative integer also. Is that okay? Because that negative integer will not give any new solution. That will give negative of the solution corresponds to positive integer. Anyway, mod psi square is same in both cases. So that's why we shall take one of them, because this is not any different thing at all. Now again, this thing you need to understand. Okay, this will be helpful for problem. Okay, you should dare to multiply wave function by minus 1. Is that okay? It will not change any physical property, isn't it? So because in any expectation value, psi star into psi would come. Am I right? That minus 1 doesn't matter for us. Okay. So that's why it will not give any new solution at all. So that's why we take only one of them. Either you can take n equal to minus 1, minus 2, minus 3, or you can take n equal to plus 1, plus 2, plus 3 and so on. What we choose? We choose n is equal to 1, 2, 3. Simply.
Sir, sir, if I will replace sin theta, sin theta divided by e to the power I theta minus theta, then it will come again.
Which one? Sin theta into
if I replace sine
Huh.
divided by
No, I mean, later also I think it will be converted into sine. Check that out. If you are writing your initial solution in terms of exponential, try to find a and b. Ultimately, you will end up with the same solution actually. Is that okay?
Yes, sir. Sir,
Yes.
yes, sir. We will again teach at this.
Huh. Whether you are talking about original solution, am I right? I have directly written in terms of sine and cosine. You are saying if we write e power I kx, yeah, then also you will end up with the same sine or cosine, okay? After applying initial condition, you will end up with the same solution, okay? So that's why, look at here, this negative integer will not give any new thing, okay? Will not give any new solution, okay? So they are again same solution. That's why we restrict ourselves to positive integer. We avoid n equal to 0, okay? So that's why, what is our wave function now? Psi of x is equal to a sine n pi x by a. Now since this function depends on this integer, I put n here. I put n here, okay? Later we shall find a. Now look at here. So once you found this k and the restriction on that n value, what is k value? Root of 2m e by h bar square. What is e? H bar square k square by 2m. Am I right? So since this k depends on integer, let me write kn here. That's the best idea. K depends on integer. Kn here, kn here, kn here. Substitute that kn. So since k depends on integer, this whole thing depends on integer. Let me write en here. Is that okay? So that en is equal to h bar square kn square by 2m. When I substitute that one, you will get en square pi square h bar square divided by 2m into a square. You got wave function, you got corresponding energy, where n should be, don't forget, 1, 2, 3 and so on. Yes, tell. That, now look at here, we don't have any control here, okay? We don't have any control over this energy. Well, you can only decide the length of the box. Possible energies are decided by the nature. Isn't it? Rest of things again, mass, particle mass will also not change, isn't it? H bar, pi, everything is constant, am I right? Now we shall normalize this one, isn't it? We shall normalize this wave function. What is this one? So now look at here. If you write psi x comma t, psi n x comma t, these are stationary state, am I right? Psi n of x into e power minus I en t by h bar, isn't it? Where psi n is this psi n now, en is this en. Earlier we have written only symbol. Now we have those values here. We have that function here, isn't it? Now look at here, normalizing this one, psi n of x comma t whole square dx, okay? Where you integrate? Actually, this wave function should be written like this, okay? Psi n of x is equal to, it's equal to a sine n pi x by a when x is between 0 to a, 0 otherwise. You should write like this, but we don't write like this because we know that this wave function, it is between 0 to a. Isn't it? Our wave function exists only between 0 to a. That's why the total wave function of a particle should be written like this actually. You should know that outside 0 to a, it is 0. But we don't quote that one, okay? We don't quote that one. In this situation, look at here, you have to integrate from 0 to a only because outside that region wave function is 0. Is that okay? Don't integrate from minus infinity to plus infinity. You should integrate from 0 to a while normalizing. Not 0 to a by 2 also, 0 to a, full region of the box. Is that okay? Because you already know that outside the region, particle is not there. There is no probability already outside the region. There is no wave function outside the region, okay? So that's why actual wave function should be written like this. Or in exam also sometimes they give So between 0 to a, its wave function is like this and it is 0 outside. They usually mention that one. Is that okay? But what we say, this is the wave function. We don't specify the region. The region should be 0 to a. Is that okay? Outside, what is the wave function outside? 0. That you should know already, okay? So now this is equal to, look at here, 0 to a mod psi n square dx. Isn't it? Because e power I theta mod square is 1. Is equal to 1. So that's why normalizing using this one is same as normalizing this one. If you normalize this one, that's done. That means normalization of time independent wave function also. This is normalizable solution because the range of the wave function is not minus infinity to plus infinity. 0 to a. Outside that one wave function is 0. Is that okay? You can normalize this one. Wait a second. Now one more thing that I haven't quoted, e should be greater than 0. Okay, when you write this one, d square psi by dx square plus 2m e by h bar square psi is equal to 0. Am I right? In this step only, write e should be greater than 0. Generally, you can write this one as some k square. Is that okay? You have written this one as k square. Do you remember? E should be greater than 0. Why? E should exceed minimum value of the potential. So that's the theorem. Is that okay? So he mentioned that one. So read out each and every sentence carefully. Okay. In this statement, you better write e should be greater than 0. That's why I am going to write d square psi by dx square. If this is positive, that positive quantity written as some k square. Psi is equal to 0. Am I right? Is that okay? E cannot be less than 0. E should be greater than 0 because minimum value of the potential is 0 in the problem. Okay. Now look at it.
In that problem, he has not specified the region of potential. So
No, any potential in that problem. That's a generalized problem. He don't say this happens only for this particular potential. Okay. That is for any potential. That 2.2 is for any potential. That okay. So he mentioned, okay, in the first page itself, by from problem number 2.2, energy less than 0 won't happen.
Sir,
Yeah.
sir, if particle touches the boundary of the box,
Particle.
No, look at here. You are thinking again classically. Particle is bouncing. It is touching the boundary, isn't it? At the boundary, you have 0 probability because wave function goes to 0, isn't it?
Tends to 0.
Yeah. You have 0 probability density.
Can I draw the graph?
You can't now imagine like it's a bouncing kind of thing. Is that okay?
If I draw the graph.
Wait a second. We shall normalize and then drop it. Okay. So mod psi n square. Mod a square outside. Sine square n pi x by a dx is equal to 1. What I am saying is normalizing this one is same as normalizing this one. Is that okay? So now mod a square. How do you write that sine square theta? 1 minus cos by 2 isn't it? Now second part is 0. You can just check that out. Cos will become sine. At the limit, at the end of the limit, you will get 2n pi or 0. Okay. So cos becomes sine. Okay. Only first part of the integral remains. That's equal to a actually mod a square by 2 into 1 dx integrals from 0 to a. That's equal to a. Do this one yourself again. That's why a is equal to root of 2 by a. You could have taken a equal to minus root 2 by a. That will not give any new answer. Is that okay? Okay. We are not going to normalize after writing this one. We are going to normalize before that one only. Okay? Because this is e power I theta. It will not change your normalization factor. Are you getting my point? The e power I theta. Is that okay? So that's why. So psi n of x, normalized wave function is root of 2 by a sine n pi x by a. That okay? And en is equal to n square pi square h bar square by 2m a square. Now look at here, a can be written as plus or minus root also, okay? Whether you write plus root 2 by a minus root 2 by a, it doesn't matter. Mod psi square is same, isn't it? Normalized wave function, eigenfunction, you can say like. Now one more thing you need to observe, h cap into psi n is equal to en into psi n. Okay? In the region 0 to a, what is h cap? Only p cap square by 2m, because potential is 0, isn't it? So p cap square by 2m psi n is equal to en into psi n. You can just check that out. So take p cap square or take that h cap operator. So what is this one? H cap in the region is minus h bar square by 2m into d square by dx square. Operate this one. Okay, you need to take second derivative, am I right? After taking second derivative, again sine function will come, isn't it? H cap psi n into is equal to same function multiplied with a constant. That is the meaning of eigenvalue equation. Can you see this one? So that's why after taking second derivative, what will happen is same function will come, some constant will come outside, am I right? N pi by 8 will come outside twice, isn't it? And one more negative sign is there, sine become cos, cos become sine, while cos becomes sine, one more negative sign will be there, negative sign will go, so that the coefficient will be this one. Yeah, just try that out. Try that out. Minus h bar square by 2m d square by dx square root of 2 by a sin n pi x by a. That's equal to first derivative will be d by dx, first derivative n pi by a comes outside, d by dx of root of 2 by a cos n pi x by a, isn't it? When you take one more derivative, what will happen? Minus h bar square by 2m, isn't it? N pi by a comes outside one more time, square, and cos becomes sine, there one more negative sign, into wave function itself. If you operate this one, you get constant time the same wave function, okay? This is psi n. Is that okay? That means we are talking about only between 0 to a, okay? H cap psi n is equal to en into psi n. Is that okay? So that's why we call this as energy eigenstate, because that's the eigenstate of Hamiltonian operator. Energy eigenvalue, okay? Energy eigenvalue. If you put it like this, then we call this a stationary state. Am I right? This is our total actual wave function actually. Am I right? No, it's a stationary state. If you substitute that psi n and en, that's our stationary state, definite energy state. Can I say like this? Okay. Yeah, these are the things that we have observed, isn't it? Now, I'll slowly move on. Remember, these wave functions are defined only between 0 to a. Outside wave function is 0. We don't quote that one every time, okay? Is that okay? Otherwise, write it like this. So, write in a flower bracket, x is between 0 to a, 0 outside, okay? Yeah. So, when this kind of thing is valid, we can't apply this one in any macroscopic situation, is that okay? In any classical situation. So now, still when this is valid, isn't it? When this is valid, the question. So now look at here. So shall I take, so adjacent energy level difference. So classically, what should be the energy? Yeah, let us have different situation here. What is your ground state? E1 minimum possible energy. What is your minimum possible energy? Why this has happened? Classically, we can keep the particle at rest, isn't it? Yeah. Why this has happened? So here minimum energy itself is again this one, isn't it? You can't mute energy. You can't mute energy, isn't it? And energy is decided by your width of the potential, isn't it? You can't have any arbitrary energy. You can have only discrete energy, isn't it? So n square, it will start from here. I think the distance will increase, okay? Quadratic in n. So E1, E2, E3, like that. Is it okay? Energy level looks like this. You can have either this energy or this energy or this energy like that, isn't it? So why? Again, uncertainty, isn't it? Suppose if you keep particle at rest in the well, what is the position of the particle? Suppose here if you keep it at a by 2, what is momentum? 0. That means you know position and momentum simultaneously, precisely. Isn't it? That cannot happen. Uncertainty will not allow, because that is the nature. Remember why it has happened? So that is the nature, okay? We can explain this one through uncertainty. Because it should follow uncertainty, that cannot happen. You can't keep particle at rest, you can't have zero energy. Is that okay? If you have zero energy means zero kinetic energy. Zero kinetic energy means zero momentum. And you are keeping that one at rest in the well, and you know what is the position. Is that okay? There is no standard deviation, isn't it, in both of them. Sigma px equal to 0. So sigma x equal to 0. What is the multiplication? 0. That is less than h bar by 2. That cannot happen. Is that okay? So that's why your minimum energy turns out to be this one. Look at here. That's the one fact. You can't keep particle at rest. Any particle at rest. Is that okay? Yeah. If you keep particle at rest, what would happen? Uncertainty will be violated. Sometimes we can say uncertainty protects quantum mechanics. Is that okay? Uncertainty, it will protect quantum mechanics. Remember, I mean, if you show something where uncertainty is violated, you can disprove quantum mechanics. Is that okay? Uncertainty that protects quantum mechanics, actually. Yeah. Now let me take second situation. Let me take adjacent energy level difference. Actually, classically, energy can be continuous, isn't it? I can write energy is equal to just p square by 2m. P can be any value. It can be continuous. Now let me take adjacent energy level difference. So En plus 1 minus En. So let me call this one as delta E, but it is adjacent energy level difference. Okay. I want to see how they are separated. Okay. How much they are separated. Because classically energy levels are not at all separated. It is continuous energy. Is that okay? So now when I see that one, look at here, what would happen? N plus 1 the whole square minus n square phi square h bar square by 2m a square. What is this one? N square plus 2n plus 1. Is it 2n plus 1? Phi square h bar square by 2m a square. Suppose for finite value of n equal to 2, 3, 4 and so on, okay? Or 1, 2, 3, 4. So this will not affect much. Is that okay? This will not contribute much to the whole equation. What will contribute? H bar, Planck constant, mass, length, width of the well, isn't it? Now let us take different situation. So first situation, suppose I am confining 1 kg mass. So I just interpreted this one, okay, in that YouTube video that I had uploaded, okay. Mass equal to 1 kg. Quickly do this one. So it is confined in 1 meter. It is confined in 1 meter. 1 kg mass is confined in 1 meter. Is that okay? 1 kg mass is confined in 1 meter. Now what is delta E? Order. Just to get me the order. So h bar square. What is h bar order? 10 raised to minus 34 joule. Yeah. What is actually order of energy? Any idea? 10 raised to minus 68. You know that one? I mean, if you convert that one into electron volt, I think you can feel that one, isn't it? So divide by 10 raised to minus 19, it will be converted into electron volt. When you divide by 10 raised to minus 19, still it is too small, isn't it? So that is almost zero. This is almost zero. So this is almost very negligible, remember. So when you confine 1 kg mass in 1 meter, this problem is irrelevant. Is that okay? This problem is irrelevant. Why? Ground state energy is zero. I mean, you can keep 1 kg mass at rest. That's the meaning. Almost at rest. So when you confine that one, is that okay? And one more thing. So there is no energy level difference. You can take this expression. No harm. Energy levels are very closely spaced. Is that okay? So now quickly let me go to second one. So mass is, suppose I am confining electron, 10 raised to minus 31 kg, 9 into 10 raised to minus 31, am I right? So now, suppose you are confining that one in 1 meter. Suppose if you have a conductor of 1 meter length, then it is confined in 1 meter. It cannot go outside the conductor. Is that okay? Electron can freely move within that one. So now also delta E, that will be nearly equal. Look at here. Now order will change. Okay, 10 raised to minus 68 divided by what is mass? So 10 raised to minus 31. A equal to 1 meter. It will not make a much difference. What is this one? 10 raised to minus 30 joule. That's also too small. Remember, divide by 10 raised to minus 19. So again 10 raised to minus 18, isn't it? Electron volt, that's too small, remember. So in this case also, energy levels are almost continuous. We can call it as quasi-continuous, okay? We shall handle this kind of problem in statistical mechanics, where our particle so to explain some specific heat of solids, we take electron which is moving in a bulk material. Then its energy level is almost continuous. Still we want to count number of energy level, okay? So that's the density of state problem. Is that okay? We'll try to count number of energy level, number of states per unit energy range. Is that okay? We are going to count that one. So that is this kind of situation, okay? It will come in statistical physics, where our material is bulk material. It is confined in a very large region, but electron. Is that okay? We are talking about free electron in a bulk material, in a large material. Is that okay? We are going to explain specific heats of solid using that one. Is that okay? Yeah, we shall come to this range later, okay, in statistical physics. Now, what is ground state again? Same thing will come. Alright, same thing will come. Again, 10 raised to minus 37 joule. It's almost zero. It's also almost zero. So now let me take third one. What is that one? Suppose electron confined in the region of, suppose, 1 nanometer, or of the order of angstrom. 1 nanometer means 10 raised to minus 9 meter, isn't it? Yeah. So now look at here, delta E nearly equal to 10 raised to minus 68 whole divided by 10 raised to minus 31 electron into 10 raised to minus 9 the square. What is this one? 68 minus 68 plus 31 plus 18. Quickly. 10 raised to minus 19, isn't it? Joule. Divide by again electron charge, you can convert that one into electron volt. Of the order of electron volt, isn't it? That does matter, remember. It does matter. Now energy levels are very well separated. So not only that, your ground state energy is sufficiently high. Look at here. Ground state energy is also same kind of approximation. That's also nearly equal to 10 raised to minus 19 joule. Order, I'm just talking about order here, okay? Not exact value. So our problem is very relevant in this situation. So, and this makes all of our, strange, properties at nanoscale. Is that okay? So different properties of the particle at nanoscale, because so they will behave like they have discrete energy levels. Not only that, energy level separation is sufficiently large, you can't mute energy. So ground state energy is sufficiently high. Is that okay?